Okay, so for gravitational fields, the first thing we kind of have to talk about is what is a field? Because we haven't talked about any field forces per se in this course. Okay? The field forces that you will deal with in physics in high school are gravitational fields, magnetic fields, and electrical fields. Okay? A field is basically an area of influence. Okay? So it's an area, or probably more accurately, a volume, okay, in which that force can exert itself on something else. It doesn't have to touch it. Okay? Almost all of the forces we've dealt with thus far in this course, with the exception of gravity, have been contact forces. So you actually had to have one object physically touching another one in order for it to exert the force on it. It was either directly touching it, like the two box questions, or it was connected by a rope or a cable or some other way for it to physically be in contact, okay, with that object in order to exert the force. Field forces don't have to do that. Field forces have the force exerted, okay, and this area in which that force can act and be felt, that's the area or volume of the field. Right? So gravity is a field strength. Right? If I jump off the surface of the earth, I'll still fall back down to it. I'm not in contact with it anymore. Okay? I'm still attracted to the earth because I'm caught in its field. Okay? Everyone follow me there? You can see that as well with like magnets. I don't know if anyone ever showed you, like in elementary school, if you put like a bar magnet down and then you put a bunch of iron filings around it, you can actually see the shape of the field. The filings will line up like this. The same thing happens with the Earth. The Earth has a magnetic field, okay? And its magnetic field looks just like a bar magnet, okay? And so there's the North Pole obviously here, okay? And the South Pole here, and then there's the magnetic field, the area of influence that repels all the god-awful stuff that the sun spits our way, okay? It's what makes the northern lights and all that kind of stuff. Okay, so it's another area of influence where the magnetic force is being exerted. Okay. Is that making sense? Okay, so that's what a field force is. That you should know. Okay, so gravitational field strength, okay, is measured as acceleration due to gravity. Okay, yesterday I was telling you that this formula here calculates gravitational field strength. Okay? And little g is gravitational field strength. So it's going to be in meters per second squared or newtons per kilogram. They're the same thing. Okay? So a newton, remember, is a kilogram meter per second squared, and a newton per kilogram, kilograms cancel, and you get meters per second squared. So either unit would be fine if you were writing that as an answer. Okay, you could write newtons per kilogram, or you could write meters per second squared. They're the same thing. Okay, so this formula here is derived, and I think I showed you this yesterday, from doing this. The force of gravity is equal to the force of gravity. That means the force of gravity I feel, my weight standing on the surface of the earth, is equal to this way to calculate it. Okay, what happens to my mass in this calculation? It cancels, because this would be true for anybody regardless of their mass. Okay? And thus it calculates the gravitational field strength or acceleration due to gravity at any given point. Okay? Everybody with me there? All right, so if we do this calculation with the numbers we have on our formula sheet, okay, what number should we theoretically get?
9.81.
Theoretically, that's what we should get, right? Okay, look on the back of your formula sheet. What does it say? It says mass of the Earth, 5.98. What does it say for Earth's radius?
6.27 × 10⁶.
Right, and it says average radius of the Earth. Okay, so that changes depending on where you are, right? Like the equatorial radius, as we saw in that video the other day, is 26 miles greater than it is over the pole. Okay, so that would calculate different numbers for G depending on where we were on Earth. Okay, so if we do this with the numbers we have on our formula sheet, we'll have 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, okay, divided by 6.37 times 10 to the 6 squared. Theoretically, that should come out to 9.81 newtons per kilogram. So it doesn't come out to 9.81, does it? Comes up to 9.83. It's close, right? I mean, is that number, are the numbers that we used in that rounded off a wee mite? Yeah, like a lot, right? Like we rounded off a ton of numbers from the mass of the Earth. We rounded off a ton of numbers from the radius of the Earth, which is squared, by the way. So if we had included all the other numbers for the radius of the Earth and squared that number, would we have been dividing by a much larger number? Would we have then got 9.81? More than likely. Okay, this is just a matter of the rounding off errors that happen mathematically. Okay, but we can see that it clearly works. Okay, we are getting a reasonable number here. Okay. So, Michael Faraday was the first person to come up with this idea of a field. Okay, and he did it with magnetic fields. He was studying that you could push a magnet through a wire, okay, like through a coil of wire. You could put a magnet through there and it would push electrons through the wire and make a current. Okay, and he couldn't figure out how that could be happening because he wasn't touching them together. There wasn't really an explanation for how are charged particles being forced to move through this wire by a magnet. And the only explanation for that was, well, the magnet, I mean, they knew metal would be attracted to it, especially iron, okay, would be attracted to it. There must be a field there that was forcing these electrons through the wire. So an area of influence, that's where the idea came from. And that really helped the idea of gravity, which up until that point was pretty much talking about invisible strings and stuff like that that were connecting everything and pulling on it and making it do weird stuff. Okay, kind of, that's how we explained everything until we came up with the idea that fields are a thing. Okay? There have to be these invisible massless strings connecting everything. Okay. So, everyone okay with that idea? All right, so is the moon caught in the Earth's gravitational field? Okay, is the Earth caught in the moon's gravitational field? Yeah, okay, they're both caught in each other's area of influence. Okay, now what happens to the field strength the further away from the center of the Earth you get? It gets weaker, right? Because R is squared, okay, it's basically the same as the force of gravity. It's the same effect, everything affects it the same way. So the further away we get, it gets exponentially weaker, right? I mean, theoretically, Earth's gravitational field is infinite, but its practical effect disappears not that far away from Earth, really. Okay, everyone all right with that idea? Okay. So this becomes a, it's fairly simple if you're just dealing with one object. The gravitational field of just a single object, completely isolated, just looks like this. Okay? The arrows represent the magnitude and direction of the field strength. The closer to the center, the bigger they are, but they all point where? They all point towards the center. Okay? Further away we get, they still point toward the center, but they get smaller. Now, if I introduce a second body into this, what's going to happen to some of those arrows? Yeah, they're going to start changing direction, right? Because now I'm going to have two competing gravitational fields. Like this. Okay, so let's say that this is the Earth and the Moon. Okay, what do you notice about the lines between the Earth and the Moon along that path? Yeah, they kind of get turned, right? And in fact, there's a point where there's no gravitational field strength right here. It's closer to the moon, obviously, because the moon is smaller, okay, and the Earth is bigger. But if I put something right there, would it stay there? Yeah, it's called a Lagrange point. Have you ever heard of those? Okay. I mean, they're proven, so it's not theoretical. I almost said theoretical. They're these points of null gravity, essentially, okay, that result from the interaction of gravitational fields. There are a number of Lagrange points around the Earth and around the solar system. And the idea is that if you could place something there, it would stay there and require no other propulsion of any kind. It would just sit there because there's a point of null gravity. Okay? And so they could be used as like gas stations to send spacecraft to other places in the solar system, because they would always be in the same place and they would move. All right, so these overlapping gravitational fields, okay, could this produce a problem if you were trying to go from Earth to the moon? Definitely. Okay, so once, if I've got a rocket and I'm headed towards the moon, there's going to come a point where I don't want the engines pushing away from Earth anymore. Why? Exactly. If I'm just using the engines all the way, there's going to come a point where I don't need the engines anymore. I'm going to be moving towards the moon because the moon's going to pull me in. Okay? And at that point, I would actually have to flip the spacecraft over and do a braking maneuver. Okay? That is, point the engines at the moon in order to slow down so that I don't go shooting past it, okay? And actually get captured and can orbit it and come back safely. Otherwise, you fly off into infinity, and that would really ruin your day. Okay? So that's something that certainly the people who plot all these courses would have to think about. Okay, there's a gravitational field of this planet. It extends out this far. Its strength at the point where the spacecraft will encounter it will be this much. That'll alter its course by this much. And that's how they plot some of those gravity slingshot maneuvers and things like that we talked about the other day. Okay, so it's an important idea, this idea of gravitational field strength. In terms of like problem solving and the math, this is an incredibly easy concept. There's only one formula, and it's this one. Okay? If you're getting a question about gravitational field strength, that's the formula you're going to use. Okay? And there's nothing tricky about it. Okay? We need to be able to understand how gravity fields work, okay? Just from kind of a practical perspective. Okay, so we've already talked about that. The lines, as you get further away, they get smaller because it's affected by the same things as the force of gravity. Is gravitational field strength the same as the force of gravity?
Well, I guess yes, because we equal G.
Okay, so force of gravity is big G times m over r squared. Gravitational field strength is big G times m over r squared. Are they the same thing? They are not. Okay, this one tells you how strongly two things are pulled towards each other. This tells you how quickly they move towards each other. Okay, so one's the acceleration towards each other. This one is the force pulling them towards each other. And force and acceleration, while similar and sharing a vector, are not the same thing. And that's the number one mistake people make on the unit exam on the gravitational field strength question. Okay? I say something about gravitational field strength and they go solving for force. Okay? Field strength and force are different. Okay? Field strength is a rate of attraction. Okay? Force is the force of attraction. How hard are they pulled together versus how fast do they move together? Those are two different things. Everyone clear on that? Okay? That's like the most important thing you need to understand about the difference between the two. Okay, so we already did this just a minute ago. So if we're looking at gravitational or equatorial radius and mass, those are numbers. I don't know if you're curious about those. I think we've looked at that chart before, actually. I would like you guys to try question number 1 and question number 2. Okay, from those those questions. So they're both gravitational field strength questions, so they're just using the formula we talked about. Okay, and these are the answers here if you want to check them as you go. Okay, obviously part A, okay, I mean it's an important thing, but we talked about it yesterday. How many Earth, if a satellite is orbiting the Earth at a distance of 3 Earth radii above the surface, how many is it away from the center? 4. Okay, that's that above the surface height or altitude trick that they play on you. Okay, so you know that your radius for question number 1 is going to be 4 times the number we have on our sheet. Okay, all right, I'll give you a little bit of time to work on 1B, and then we'll go through it together. Okay, let's have a look at number 1 here. Okay, so in number 1 we know Earth is the mass, okay, and we know 4r is the Earth's radius, or the orbital radius for this question. So we're just going big G, or little g equals big G times the mass of the Earth over r squared. So that'll be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24. Okay, divided by 6.37 times 10 to the 6 times 4 squared. Okay, so when we're punching that into our calculator, that's how it'll have to look. So missed the decimal. Okay, so slightly different number there, and that's because their mass of the Earth and their radius of the Earth are slightly different numbers than the ones on our formula sheet. Okay, so if you got 0.614, you're good. Okay, you did it right. Okay, how are we doing on number 2? How many people have done 2? Okay, I'll give you a few more minutes there on number 2. Okay, so we're looking for the gravitational field strength at the location of the astronaut, and what the magnitude of the gravitational field strength would be if they were orbiting the moon at the same separation distance. Okay, so substitute mass of the moon for mass of the Earth. Okay, 7.36 times 10 to the 22. I don't know if that number's on your formula sheet or not. Okay, so what are the 2 tricks in question number 2?
The distances in kilometers.
Distances in kilometers is one of the tricks, so you need it to be 10 to the 7 in meters. And what's the other one?
Mass of the astronaut.
Yeah, you don't need the mass of the astronaut. It's just there to throw you off. And I'll bet it threw a few people off because I used to put a question just like this on the unit exam, and I bet you 1/4 of people would plug 80 in, get a ridiculously small number for gravitational field strength, and I mean like beyond ridiculously small, because the gravitational field strength of an 80 kilogram person is nothing, okay? And they would write that down as the answer for the gravitational field strength on the surface of the Earth for an 80 kilogram person. Okay? So we got to make sure our answers make sense when we're doing them. Okay, kind of checking our work as we go there. So for this one here, okay, all we're doing is we're changing out this number here to be that number they gave us in kilometers. Okay, so that's we're looking at 3.2 times 10 to the 7. Okay, because we're still talking about being around the Earth. Okay, so if we want to shortcut that on our calculator, we'll just go 3.2, 0, and it's 7, not 6, and we'll delete everything else. Okay, 0.389 newtons per kilogram. Should be our answer there. And then if we wanted to do this with the moon, we do exactly the same calculation. We just substitute the mass of the moon. Oh, no. Maybe that's not the faster way to do it. So 7.36. Okay, 0.0479. Yep. Everybody all right with those? Okay. For question number 3, do they do the same thing? Oh, actually, sorry. Question number 3 is a trick question. What are they asking you for in question number 3? At the highest satellite to orbit Earth at a distance of 6.6 Earth radii from the Earth's center, what would be the gravitational force on a 70 kilogram astronaut? What's that? No, it's actually, you actually have to do a calculation here, and it's the gravitation. If it was the field strength, you'd be right. What are they asking for? Gravitational force. Now you're looking for FG, not little g. It's a one word, right? We changed one word in that question, and suddenly we have to solve it in an entirely different manner. Okay, that's the thing to watch for. It's really easy to confuse a universal gravitation question with a gravitational field strength question if we're not careful. Okay, so that's all I wanted to illustrate with that one. Okay, now, part A of this question, I love this question. I use it periodically on this unit exam. What is the mass of a 60 kilogram student on Mars and on Earth? 60 kilograms. That would be a 1 mark question. That's why it's a multiple choice question. But I would put in the answers for their weights on both, and then D would be like impossible to tell or something like that. Okay? You would be shocked how often I get people doing the calculations, calculating what it would be on Mars, calculating what it would be on Earth, finding those numbers as a multiple choice answer because I'm a jerk and I put them in there, okay? And then getting the question wrong, and then when I go through it, I'm like, mass, what's mass, right? Your mass is your mass. No matter where you go, you are 60 kilograms. Okay? That's why I love that question. Okay? It's that question that asks, do you understand the difference between mass and weight? And I find out, unfortunately, that lots of people don't understand the difference between mass and weight. Okay? Now, what's the student's weight at the equator on the surface of Mars and Earth? That's a different question. That would be a universal gravitation question, not a field strength question. Because field strength calculates acceleration due to gravity. Weight is the force of gravity. So again, it's those little changes in the wording, okay, that can make this question totally different. All right. Let's have you guys do 1 and 2. Okay, give you a few minutes on 1 and 2. Okay, so for question number 1, am I looking for force of gravity or gravitational field strength? Force of gravity, it's asking for weight. Okay, so for that one there, I would plug in the numbers that they've given because it was for Saturn. So that would be 6.67 E negative 11, then the mass of the dog, and then the mass of Saturn, 5.69 E 26. Okay. And then divide that by the radius of Saturn, 6.03, 7 squared. squared. Okay, so that would be their weight in newtons on Saturn. That would be their weight in newtons on Earth. It's not that different, is it? No. Why? Saturn's way bigger.
The mass isn't, the dog is not that like high in significance, so it means that the two objects aren't pulling together as hard.
I mean, yes and no.
Saturn's a little bit bigger, so it pulls a little bit harder than the Earth would, but the dog is still the same, has the same mass, so it would pull as equal.
No, it wouldn't have to do with the dog, because then I would feel the same way. If I went to Saturn, I'm not going to feel significantly heavier on Saturn either. Right? But Saturn's huge. Shouldn't I feel a lot heavier?
Is it like the velocity that like Saturn travels at?
No, but it does spin really fast. It's because Saturn's not dense. Okay? Saturn's massive, way more massive than Earth. Okay? It's times 10 to the 26, we're times 10 to the 24. Okay? Saturn is way bigger, but it's also way bigger. Okay? Its diameter is also a lot bigger than the Earth's, so Saturn's quite light. In fact, it's so light that it would float if you had a bathtub big enough to put it in. Okay? So Saturn, even though it's very, very large, it's not very, very heavy for that size. That's why you wouldn't be crushed on Saturn, okay? Because Saturn's, for its mass, also quite large. Okay? Whereas for Jupiter, okay, Jupiter you would have a problem, okay? Because on Jupiter, if we did this thing here for your weight on Jupiter, okay, do you think your skeleton could support your weight? Rather than calculate my weight on Jupiter, I'm just going to calculate the gravitational field strength on Jupiter and compare that to 9.81. Okay, so I'm going to go 6.67 e negative 11. Okay, and then the mass of Jupiter is 1.9 e 27. Whoop. And then the radius of Jupiter is 7.15. Whoop, I need a bracket there. Okay, so on Jupiter, the acceleration due to gravity is almost 25 meters per second squared. On Earth, it's 9.81. It's a lot different, yes? Like 2.5 times different. I'm going to feel 2.5 times heavier. Am I going to want to walk around like that all the time? Absolutely not. Okay? Now, is it going to crush me? No. It's not the gravity that's going to crush me on Jupiter. It's the atmosphere. Okay? The weight of the atmosphere above. It's the atmospheric pressure. Okay? The atmospheric pressure would crush me. Okay? Not my weight. Okay? The weight of the atmosphere would crush me. All right, so on Monday, you will get your gravitation assignment, right? So it'll be just this stuff, and you'll have the whole class. You'll have the whole class to work on it, and you'll probably get it done because it's not super difficult. You'll probably get it done in class, and then you got your unit exam on Wednesday, which we reviewed for yesterday. So Tuesday, we will start simple harmonic motion.
So, for the, like when you're looking for the force of attraction for like animals, how would you, like do you keep
So I have a
all
social
the
diploma.
masses, so it'd be
When
like
we get back to
big G, and then the mass of whatever, like Saturn in that case, and then mass of the astronaut,
Yep.
and then R. What would you do with the other ends? Because if it's FG, which is...
FG, you got your two ends. Saturn and the astronaut, those are your two ends.
I know, but like if it's FG
Can't be an
equals
engineer.
FG, the one side has MG.
Yeah, that's the mass of the small body.
And so I could just put 700.
So, like, I was only showing you that to derive, so you could see how to derive it. When I did this,
What you needed for
This is mass, that's where that formula comes from.
I just real 95%.
And then it'd be GM.
Yeah, so for this one, for calculating gravitational field strength, I use the body generating the field. That's the larger one.
But like for the dog example,
The dog example, I wasn't using that formula.
you were using one.
I was just using this formula.
Fact check something.
Aren't they technically the same? You still have
No, in this formula, I set this formula equal to that one. In the Saturn question, I was just looking for that number.
Oh, so you treat FG as a whole, not divided into M and G combined.
Right.
Oh,
Yeah?
that makes sense.
Okay.
Because I was treating it like M and G.
Okay, I
And I was
get
doing
you.
big G and all that. So
Yeah.
that's why I still got them canceled out.
Right.
Okay, that makes sense.
Okay.